check if the sound is, देखिए sound आ रहा है क्या? आवाज आ रही है? Okay. All right. So students, today we are going to do rotational motion. Let us begin. So the topics that we will be covering is moment of inertia, torque and angular momentum, and angular momentum conservation. And another topic that we'll do is rolling motion. Okay, so these are the topics that we'll be covering today. So let us begin by understanding what is a rigid body. So rigid body is any body whose distance between any two points should remain fixed. Suppose this is point A in the body, this is point B in the body. The distance between them should remain constant. It should not change. That means the body cannot be compressed or extended. Okay, so this is what is a rigid body. So you can see rigid body is defined as a system of particles in which distance between each pair of particles remains constant. So this is what is rigid body, and rotational motion is also known as rigid body dynamics. In this chapter we will be dealing with rigid bodies. Now, what are the types of motion that a rigid body can do? So there are three types of motion. First is the pure translational motion. Okay. Next is pure rotational motion. And the third one is combined translational as well as rotational motion. So pure translational motion, pure rotational motion, just like a circular motion, and combined translational and rotational motion. For example, the wheel of a car. Okay. Let us begin with this. First of all, our main topic here is the first topic, moment of inertia. So just like mass gives an idea of translational inertia. For example, more the mass, greater is the effort required to move the body. Similarly, moment of inertia gives an idea of rotational inertia. So more is the moment of inertia, more is the effort required to rotate the body. So moment of inertia, it is a measure of rotational inertia by virtue of which it opposes the changes in its rotational motion. For a point mass, suppose I say we have a point mass m from an axis at a distance r, then its moment of inertia about this axis can be given as m into r square. Mass into distance from axis square. And for multiple masses, for multiple point masses, we will just keep on adding the mr square. So summation mr square, where r is the perpendicular distance from axis of rotation. What about continuous mass distribution? So suppose this is an axis and this is a body with continuous mass distribution. Mass is continuously distributed throughout the body. Now, In order to find its moment of inertia, we need to consider a small elemental mass dm whose distance from the axis is suppose r. So the small moment of inertia of that mass, the point mass, can be written as dm into r square, and the net moment of inertia will be just given by the integration of this, that is integration dm r square. So this is how we can find the moment of inertia of a continuous body where there is continuous mass distribution, whereas this is how we can find the moment of inertia of point masses. So I hope that is clear. Okay. Okay, moving forward. So the unit of moment of inertia is kg meter square and its dimension is ml2. It is a tensor quantity, that means it has direction. Okay, it has a directional sense, but it does not follow vector law of addition. So it is a tensor quantity. What does moment of inertia depend on? It depends on the shape and size of the body. Okay, the mass distribution in the body, and it depends on the position of axis of rotation, how the axis of rotation is located. This is asked many times in NEET. All right, we have a small question. In this, which of the following option is correct? Which of the following option is correct here? All right. So which of the following option is correct regarding moment of inertia? So if you see here, we know moment of inertia is summation mr square, right? So I can just say m1 r1 square plus m2 r2 square. Basically, it depends on the mass also and as well as the square of the distance also. If you see here, wood is obviously lighter than steel. Steel is much heavier and steel is farther away from the axis. So its moment of inertia will be greater here. Whereas steel's moment of inertia will be lesser here. Same goes for wood also. Wood's moment of inertia will be lesser here and greater here. But wood has lesser mass than steel. So placing steel away from the axis will increase the net moment of inertia much more. Hence, I can say that in the first case, the moment of inertia is greater. Okay, moving along. Next, we have perpendicular axis theorem. What does perpendicular axis theorem say? So, suppose we have this body and it is only applicable for two-dimensional bodies, also known as planar bodies. This theorem is only applicable for 2D bodies, not 3D bodies, remember. Now, suppose we have a body, which is, you can see here, and let's say X and Y are two axes within the plane of the body. Okay. Let the moment of inertia about X axis be I1, the moment of inertia about Y axis be I2. Again, x and y axes are in the plane of the body. Moment of inertia around about x axis is I1, and let's say about y axis is I2, and about z axis is I3. Then perpendicular axis theorem says that I3 will be the sum of I1 and I2. Okay, I3 will be the sum of I1 and I2. So some points here. I1 and I2 should lie, the axes should lie within the plane of the body. Second point, the axes which lie in the plane of the body, they must be perpendicular. And third point, the axis I3 is perpendicular to the plane of the body, okay, and passing through the intersection point. For example, if I consider this copy, so suppose this is one axis I1 and this is another axis I2, okay, so this is I1, this is I2 within the plane of the body, and they are perpendicular. So about this axis, about their point of intersection and perpendicular to the copy, about this axis, this is I3. So I3 will be equal to I1 plus I2. This is perpendicular axis theorem. So I hope this is clear. All right. Let us see a question. A lamina lies in the xz plane. Okay. Okay. So xz plane. So which is the perpendicular to this y-axis? Its moment of inertia about x-axis is 40, and about y-axis is 120. Then find its moment of inertia about z-axis. So obviously we will apply the perpendicular axis theorem here. So we can write Iz equals to Ix plus Iy, sorry, Iz about y-axis is this much, then okay, my bad. Iy, because y is the one which is perpendicular, right? So Iy equals to, we know, Ix plus Iz, and we need about the z-axis. This is given as 120, this is given as 40. So about z-axis it comes out as 80. This is the answer. Okay. Next we have parallel axis theorem. Now, perpendicular axis theorem only valid for planar bodies, but parallel axis theorem is valid for all types of bodies. Okay, 2D, 3D, all types of bodies, parallel axis theorem is valid. So let us understand this. So suppose we have a body, a 3D body, and here is the center of mass of the body. This is an axis passing through the center of mass, and about this axis the moment of inertia is ICOM. Now this is another axis parallel to this axis. Okay, let's say the moment of inertia about this is I, and let's say the perpendicular distance between these two parallel axes, the perpendicular distance is D. So parallel axis theorem says that I, this moment of inertia about this axis, shall be equal to ICOM, about the center of mass, plus, let's say m is the mass of the body, so plus md square. Is that understood? This is parallel axis theorem. I is equal to ICOM plus md square. All right. Now we will write down some moment of inertias that we need to memorize. Okay, we have to memorize these formulas for the examination. So for a rod, so let's say this is a rod of mass m, length l. Axis passes from the edge. This is an axis passing through its edge. The moment of inertia about this will be ml square by 3. We need to memorize this. What about the axis passing through this end? Same. This is also ml square by 3. What if the axis is going into the board like this through the edge? Again same. Ml square by 3. Okay. Axis passing from the center. So what if the axis passes from the center of the rod? Rod mass m, length l. This moment of inertia is ml square by 12. We need to memorize this. Again, if the axis passes through the center into the board, doesn't matter, it is still ml square by 12. Next, ring. Next we have a ring. So for a ring, let's say this is a ring of mass m and radius r. Axis passing from center and perpendicular to plane. This axis. About this axis, the moment of inertia is simply mr square. Okay, we just need to memorize this. Again, for a ring, if axis passing from center in the plane, okay, this axis we need to find. We can use perpendicular axis theorem to do this. See, this is something which we need to find. Let this be I. I create another axis in the plane passing through the center. If this is having moment of inertia I, this will also have I, right? And what is this moment of inertia? We have just written it in the last slide, mr square. So now we will apply perpendicular axis theorem, and this should be equal to this plus this. So mr square is equal to I plus I. So moment of inertia comes out here as mr square by 2. Okay. So this is how we can use perpendicular axis theorem to find moment of inertias in many cases. The next, let's see. For a disk, axis passing from center and perpendicular to the plane. So this is a disk, mass m, radius r, and this is the axis. So about this axis, just memorize this result. It is mr square by 2. Okay, mr square by 2. For a disk, axis passing from center and in the plane. So similarly, just like we solved for ring, we can solve for this also. Let this be I. This is what they are asking us. So this is also I, symmetrical axis. And this we know has value mr square by 2. So now this can be written as I plus I, 2I. So what is moment of inertia value here? I, it is mr square by 4. Is that clear? Next we have hollow sphere. So hollow means inside it is empty. It only is the surface. So hollow sphere, axis passing from center, let's say mass m radius r. So the moment of inertia here is 2 by 3 mr square. And any axis passing through the center will have the same moment of inertia. Any axis passing through the center will have the same moment of inertia. Next is solid sphere and axis passing from center. Similarly, it is 2 by 5 mr square. Again, this is also the same. This axis also the same. 2 by 5 mr square. You will have to memorize these results. And you can definitely expect one question in NEET from moment of inertia topic. It's a very important topic, very cost effective topic. For solid cylinder, an axis is passing from axis is this, the axis of the cylinder. This is a solid cylinder, mass m, radius r, and length l. About this axis, the moment of inertia is simply mr square by 2. Does not depend on the length. Okay. Again, hollow cylinder and axis is the axis of cylinders. So again, let us build a hollow cylinder. Hollow means, again we know this, inside is completely empty. So mass m, radius r, and length l. So about this axis is passing from axis of cylinder. So this axis moment of inertia is mr square. Is that understood, everyone? Now we have a question. Let us try to do this question. So it's given that two rings have their moment of inertias in the ratio 4 is to 1. So we have two rings and their moments of inertias are in the ratio 4 is to 1. And their diameters are in the ratio 4 is to 1. If diameters are in the ratio 4 is to 1, radiuses are also in the same ratio. We have to find the ratio of their masses. So for ring, I can write this as m1r1 square. Sorry, yes, m1r1 square by m2r2 square, because for ring it is simply mr square moment of inertia. r1 by r2 can be written as 4. right? R1 by R2 whole square. So ratio of masses comes out as 1 by 4. So this should be the correct answer here. All right. Next topic we have is radius of gyration. Very small topic, but frequently they are asking us questions on this. So suppose anybody has moment of inertia about any axis as I, its mass is m, then the radius of gyration is defined like this: root I by m. You can also rewrite this moment of inertia I as mass of the body into radius of gyration square. This is another way. So k comes out as under root moment of inertia by mass. So it is dependent on axis. This radius of gyration is dependent on the axis. Okay, we can see here. What does it depend on? Firstly, axis of rotation, and secondly, the mass distribution, because moment of inertia will change if mass distribution changes. So radius of gyration will also change. But radius of gyration does not depend on mass of the body or angular quantities like angular displacement theta, angular velocity omega, angular acceleration alpha, all those. So important points can be asked in NEET exam. Next is torque. So what is torque? Torque is something which causes rotational effect. So suppose this pen, it is hinged at this end and I apply some force. So this pen will try to rotate, right? So this rotational effect is created by something called as torque. You can see here in the diagram that if we have a wheel and we exert a force like this, the wheel will start to rotate. Even a door is hinged about this, and if I exert some force here, the door will swing, it will open or close, so it will rotate about the hinges. So torque is something which creates rotational effect. Now what is the mathematical expression for it? Let us see that. Okay, so suppose a force is acting at a particular point. Okay, and we need to find the torque of this force about this point. Force is acting at this point, and we need to find the torque of this force about this point. Then we create a vector called position vector r vector. Its head is on the point where force is acting, tail is on the point where we need to find the torque, and the torque of this force comes out as cross product of r and f. So tau is given by the cross product of r vector and f vector. There is one more way you can write the torque. You can also write the torque as moment of inertia into angular acceleration I alpha. This is just another way of writing torque. All right. Let us move forward. Unit of torque. So it is force into displacement, so the unit is simply Newton into meter. Newton into meter. Or we can also say it is simply Dian into centimeter. Force into displacement, Dian into centimeter. Its dimensions are ml to t minus 2, frequently asked. Okay, this question, uh, the sometimes they come like units in measurement question. Which of the following options have the same dimensions? So if you see here, this dimension is the same as energy. Energy also has the same dimensions. Okay, probable question. Okay, next topic is angular momentum. What is angular momentum and how do you define it? Look at the board. This is mass m. Suppose it is moving with a velocity v vector. We want to find the angular momentum of this mass about this point. So this is the position vector of this mass with respect to this point. Now its linear momentum is defined as mv. And how is angular momentum defined? Angular momentum is defined as r cross linear momentum. R cross linear momentum. Linear momentum is itself mv. So if you put that value here, we can also take m outside and we can write it in this manner. This is also equally correct. This is also completely correct. Angular momentum for a point mass. All right. Angular momentum of a rigid body rotating about a fixed axis. Okay, so suppose we have a body which is rotating about this axis, let's say like this. Okay, let's say about this axis the moment of inertia is I and it is rotating with angular velocity omega. So its angular momentum about that axis is defined as I omega. I omega. This is another way to write angular momentum. Usually it is used for rigid body, continuous mass distribution. Usually it is used for that. Before we proceed further, there are a couple of other formulas I want to tell you. Torque can be written as rate of change of angular momentum. Torque can be written as rate of change of angular momentum. What else? There is something known as rotational kinetic energy. Translational kinetic energy, I'm sure you are aware of, half mv square. This is rotational kinetic energy, half I omega square. Kinetic energy of rotation or rotational kinetic energy. Now, rotational kinetic energy can also be written as angular momentum square by 2I. Angular momentum square by 2I, or angular momentum can be written as under root 2I kinetic energy of rotation. Okay, both ways you can write it. So these are some other formulas that we should remember. Very common questions come from these formulas. Okay, any doubts still here? Let me just check the comment section. All All right. Next is conservation of angular momentum. So, see, we know torque can be written as rate of change of angular momentum. If the torque acting is zero, which means dl dt is zero, differentiation of something is zero when that something is a constant. Therefore, initial angular momentum is equal to final angular momentum, and this is known as conservation of angular momentum, and it applies only if torque is zero about the same axis. So if torque is zero, angular momentum is conserved. If force is zero, linear momentum is conserved. All right. Moving forward, let us see a question here. Two wheels A and B are placed coaxially. Wheel A has moment of inertia LA and angular velocity omega A. Okay. So moment of inertia is LA instead of IA. They have given us LA. Okay. Actually, it should be IA. Let us just change it to IA. Moment of inertia IA. Angular velocity is omega A. B is stationary. Okay. So omega of B is 0. On clubbing them with a clutch, okay, they are now attached. So they move jointly. Now both are moving with omega. Now both are moving with omega. Then the moment of inertia of B is. So IB is something they are asking us. So this can be solved by the help of angular momentum conservation, as the torque about this axis is going to be 0. So initial angular momentum equals to final angular momentum. Initial composes of both A and B, final also composes of both A and B. For initial, I can say angular momentum of A plus angular momentum of B is 0. And for final, I can say the total moment of inertia into the omega. Now this is what we are required to find, so we can very easily find this. IB comes out as IA omega A by omega minus IA. We can even take that common, and this brings us to the answer. A very simple application of angular momentum conservation. Moving forward, next topic that we have here is rolling. Rolling without slipping, pure rolling. Okay. Now, this is combined translational and rotational motion. Rotational and translational combined motion, just like the wheel of a car, just like when a car moves. So, to analyze a body under combined translational plus rotational motion, we need to analyze the body's motion in two parts. First, we need to see the motion of the center of mass, and then superimpose the motion of body with respect to the center of mass. So for combined translation plus rotational motion, we need to combine these two. Only the motion of center of mass plus the motion of body with respect to center of mass, and then we can see the combined effect. So here we have a body which is moving forward with speed v and rotating with omega, and let's say the body has radius r. Okay, so how do we analyze the body? All right, so first, the center of mass is moving with v, so motion of center of mass. So I am interested in finding out the speeds of these four diametrically opposite points. I want to see the speeds of these points. Center of mass motion is directly imparted to these points, so they are all moving with the same, in the same manner. Okay, so center of mass motion is my bad, center of mass motion is directly imparted to all the bodies in the same direction with the same velocity. And now comes the rotational motion part. So it is rotating with omega, it is rotating with omega, so tangential velocity will be there as r omega, tangential, so it is simply added. Yes, here the tangential r omega is going to be like this, here the tangential r omega is going to be like this, and here it is going to be in this direction. Yes, now in case of pure rolling, in case of pure rolling, v is equal to r omega. This is something you need to memorize. Also, acceleration is equal to r alpha. So these two relations we need to memorize for pure rolling. So instead of r omega, I can also write as v, because this is simply equal to v. Yes. So if I do that, if I do that, and if I write the final velocity of these points, so if you see here, uh, if you look here, this point has speed 2v, because r omega is also v plus v 2v. This point has v speed like this and v speed like this, so the net speed comes out as root 2v, right? What about this point? The bottommost point, the v and v got cancelled, so this linear speed of this point is 0. And what about this point? V like this and v upwards, so root 2v in this manner. So when it is performing, when this body is performing combined translational plus rotational motion in pure rolling, then the four diametrically opposite points will have this much speeds. And we've just found it by using this thing. Motion of the combined motion is equivalent to motion of center of mass plus motion of body with respect to the center of mass. All right. Now let us try to write the total kinetic energy of that purely rolling object. So if a object is doing pure rolling, V omega and V equal to R omega, then its translational kinetic energy is written as half mv square. Its rotational kinetic energy is written as half I omega square. So its net kinetic energy is half mv square plus half I omega square. So this is the total kinetic energy of a purely rolling object. However, we can write this in different forms. So let's say about this axis, the moment of inertia, mass and radius are obviously. Moment of inertia is written as uh, mk square. Moment of inertia is written as mk square, where k is the radius of gyration. Okay. So this value mk square can be substituted here. Also, v equal to r omega can also be substituted here. And in this manner, we can reduce this formula further if we like. But no need to memorize that. That should be done in practice alone. Okay, fraction of total kinetic energy in other form. So let us understand this by an example. Suppose we have a solid sphere. We have a solid sphere m, let's say 5 kg, or just let me just take it as m and radius r, and it is doing pure rolling. It's going forward with v and rotating with omega, and v is equal to r omega. Pure rolling is taking place. Then we can write its translational kinetic energy as half mv square, its rotational kinetic energy as half I omega square. Now what is its moment of inertia? Moment of inertia here is 2 by 5 mr square, right? And omega can be written as v by r, and omega square, so v by r whole square. If you see here, the r square gets cancelled and we get the rotational kinetic energy as simply 1 by 10 mv square. 1 by 10 mv square. So fraction of total energy. So what is the net energy first of all? If you see, the net energy will be translational plus the rotational energy. So half mv square plus 1 by 10 mv square. So this will come out 6 by 10 mv square, or simply 3 by 5 mv square. You can also write it k net as 3 by 5 mv square. Now, fraction of total kinetic energy in other form. So, if I were to find how much fraction of translational kinetic energy is there in the net kinetic energy, I'll have to find this ratio, translational by net. So if you see here, translational is half mv square, net is 3 by 5, so you will have half divided by 3 by 5, so you will have 5 by 6. Yes. And if we were to find the rotational energy in the net energy, then we will divide 1 by 10 by 3 by 5 and we get it as 1 by 6. So this is how we can find fraction of total kinetic energy into other forms. And this is a very, very popularly and commonly asked type of question in NEET exams. So I hope this is clear to everybody. Okay, let us see a question here. So this is the same question that we have just done. Okay, solid sphere is rolling in rolling motion, body possesses translational as well as rotational energy simultaneously, and they're asking us translational by translational by translational plus rotational. Okay, so this is a question that you can try at home. All right, this is a question which you can try at home. Now we will begin with PYQs. Okay, NEET PYQs will be doing that. We will be seeing what type of questions NEET is asking us and how we should solve them. But we will take a short 5 minutes break and then we shall continue. All right, students, let us solve NEET PYQs. So now we have entered the PYQ segment. So this question was asked in 2025 NEET exam. The sun rotates around its center once in 27 days. Time period of rotation of sun is given. What will be the period of revolution if the sun were to expand to twice its present radius without any external influence? Without any external influence, so net torque is 0. So angular momentum is conserved. L initial equals to L final. Assume the sun to be a sphere of uniform density. Okay. So this is I1, I initial, omega initial, I final, omega final. Now if you see, moment of inertia is 2 by 5 mr square for solid sphere, or I can say it is just proportional to mr square. Now mass is not changing, only radius is doubled. So I can say I is just proportional to r square here. Radius is doubled, so final must be 4 times of initial, right? So I can say omega initial is 4 times of omega final. Okay. Omega can be written as 2 pi by time period. So from here we get the final time period as 4 times the initial time period. Initial time period is 27. So this comes out at 108. So the correct answer here is option D. So this question is based on angular momentum conservation. All right. Coming to the next question. So this question says that the situation is something like this. Okay. So there is a ladder or rod. This is the rod. Okay. Its mass is given as 20 and length is also given 5. Leans against a smooth vertical wall. There is no friction here, making an angle 60-degree with it. Okay. The other end rests on a rough horizontal floor. Friction is available here. The frictional forces that the floor exerts on the rod. Okay. So let us draw the forces. First of all, a normal reaction from here, a normal reaction from here, mg from the center of the rod, and frictional force this side to prevent it from slipping. It is in equilibrium, so I can say N1 is simply equal to mg equals to m is 20, so g10 200, whereas friction is equal to n2. This is translational equilibrium. Now if we do rotational equilibrium, suppose about this point, so we will say that the net torque about this point is 0. This force is passing through the point, its torque is already 0. This force is also passing through it, its torque is already 0. But these two forces will create torque here equal and opposite. and that will get balanced. So if the net torque is 0 about this point, the n2 into the perpendicular distance is, if this is L, L cos 60. So I can say n2 into L cos 60, this is the torque of n2 about this point, is equal to n1 into, mg into, my bad, mg into, this is L by 2, right? And this is 30 degree, and this is the perpendicular distance. This is to be L by 2 cos 30. So mg into L by 2 cos 30 degrees. Okay, and N2 is nothing but friction. And if you solve this equation, you will get the value of friction as 100 root 3. Friction, that means N2, as 100 root 3. So the correct answer here is option B. I hope this is understood. Okay, equilibrium question. It is also asked in the year 2025. Let us see another question here. The wheel of a bullock cart is rolling on a level road as shown in the figure. Okay, if its linear speed is v in the direction shown, which one of the following options is correct? P and Q are highest and lowest points. Okay, we have just seen this in pure rolling. Do you remember? This moves with 2v and this speed is 0. So which option should be correct here? Option B. Point P moves faster than point Q. Simple question, 2024 NEET. Moving to the next question. The ratio of radius of gyration of a solid sphere of mass m and radius r about its own axis to the radius of gyration of thin hollow sphere, same mass, same radius. Okay. See, it's very simple. We know moment of inertia of solid sphere is 2 by 5 mr square. We can write it as m k1 square. So k1 comes out as how much? Root 2 by 5 r. For hollow sphere, it is 2 by 3 mr square. It can be written as mk2 square, radius of gyration k2. So k2 comes out here as under root 2 by 3 r. Now the ratio of radius of gyrations k1 by k2 is, it will come out as root 3 by root 5. So the correct answer here is option C. A very simple question, and they have asked this in the year 2023. Moving to the next question. So in this question, a rod is there and it has length 200 centimeters. So its center of mass is here. at 100 centimeter mark, and mg shall act from here. Let's not call it mg because m is here. So its mass is 0.5 kg. If you see, it's given here. So mg, g is 10, so mg will become 5. Anyways, so the balancing is done on the wedge. So net force is 0, net torque is 0. Okay, 2 kg is suspended from here, and m mass is suspended from that point. We need to find m so that the rod is in equilibrium. A very simple question. We shall conserve, we shall equate the torque about this point. We shall say that torque is 0 about the wedge. If we do that, what is the torque here? 2 kg, so 20 mg is 20, and this distance is 20 centimeter or 0.2 meters. In meters it is 0.2, equal to, this distance is 60 centimeter or 0.6 meters. 5 into 0.6, and now this force here is mg or 10m. And what is this distance? The distance here is 160 minus 40, 120 or 1.2. So I can write it 1.2 into 10m. Now we can just solve this equation and we will see that the answer comes out as 1 by 12 kgs. Option C is correct here. This was asked in NEET 2021. Okay, all right. Let us continue. So a very simple question here, and it was asked in 2020. Find the torque about the origin when a force of 3 joule, 3 j cap Newton acts on a particle whose position vector is 2 k cap. So if you want to find the torque, we know the simple formula of torque as R cross F. R has been given to us as 2 k cap and force is 3 j cap. 3 to just 6. K cross j is minus I cap. So the answer comes out as, must be a printing mistake. This is supposed to be I cap. It's a printing mistakes, and the answer here is option B, minus 6 I cap. I hope this is clear. All right. Let us see the next question. Again 2020. Angular speed of the wheel has been increased from 360 from 360 to 1200 rpm in 14 seconds. So if the frequency is given, what is omega initial? 2 pi f by 60, and f should be in rotations per minute. So if you see here, omega initial will come out as 2 pi into 360 by 60. Omega final will come out as 2 pi 1200 by 60. Okay. So what is its angular acceleration? Alpha. Omega final minus omega initial by t. So very simple formula here. If you put these values and solve this, the answer which you will get is simply 2 pi. So the correct answer here is option D. All right. All right. Next question was asked in 2018. Solid sphere is in rolling motion. In rolling motion, a body possesses translational as well as rotational energy simultaneously. The ratio of translational to total, that is translational plus rotational. This ratio they are asking us. So let us try this. Translational is simply half mv square. Rotational is half I omega square, right? Now, moment of inertia for solid sphere is 2 by 5 mr square, and v omega is v by r. So rotational comes out as 1 by 5 mv square. Okay. So what is the total? So let us just put this value. Translational is, okay, kt by kt plus kr. So this is half mv square. And what is do we have in the denominator? We have half mv square and rotational 1 by 5 mv square. So if we solve this is half mv square, and if we add this 7 by 10 mv square, so we are going to get 5 by 7. And do we have that? Yes. Option B is the correct answer here. Moving to the next question. So we have been given 2 points here, 2 comma 0 comma minus 3 and 2 comma minus 2 comma minus 2. A force is acting at this point. We have to find the torque about this point. Torque has to be found about this point. So this is my r vector. This is my r vector. What will be r vector? Final minus initial, 0 I cap gone, 0 minus minus 2, 2 j cap, minus 3 minus minus plus, so minus k cap. So this is my r vector. Let's check again. This minus this 0 I cap, 0 minus minus 2 plus 2 j cap, minus 3 plus 2 minus k cap. And now we can easily calculate torque. So torque will come out as R cross F. We can use the determinant method to solve this. So we can put the values of I cap, j cap and k cap. For R it is 0, 2 and minus 1. For F it is 4, 5 and minus 6. So after solving, if you solve this, you shall get the answer as minus 7 I cap, minus 4 j cap, minus 8 k cap, which is option D. So simple determinant method, we have to do the cross product and we'll get the answer here. 2020 question. We shall take a break of 5 minutes and then we shall continue. Till then, you can try to solve this question which was asked in 2017. All right, students, so I hope you are able to solve this question. What is it saying? We have a hollow cylinder and a rope is wound on top of it. Okay, a rope is wound on top of it. The cylinder has mass 3 kg and radius 40, so 0.4 meter. What is the angular acceleration of the cylinder if the rope is pulled by a force of 30? So it's very simple. Torque is F into the radius, and this can be written as I alpha. What is I here? The I moment of inertia is hollow cylinder, so mr square. So we can write this as F into R as mr square alpha. So from here alpha we will get F by m into R. F by m into R. F is given as how much? F is given as 30, m 3 kg, and radius we have seen 0.4. So the answer will come out as 25. Option B is correct here. Simple question asked in 2027. Sorry, 2017. Maybe it will be asked in 2027. You never know. All right, let us go to the next question. A thin uniform rod of mass m and length L. So we have a rod, mass m, length L, is rotating about a perpendicular axis passing through its center. So we have an axis passing through its center and it's rotating about this axis with constant angular velocity omega. Constant omega it is rotating. Okay. So what happens after that? Two objects each of mass m by 3. Two objects each of mass m by 3 are attached gently to the two ends of the rod. The rod will now rotate with how much omega? So the thing is, angular momentum is conserved here. So initial angular momentum equals to final angular momentum. So I initial omega initial is I omega only, right? Equals to I final omega final. What is I initial? I initial is mass m, right? Uniform rod m L square by 12. And what is I final? Now masses are also added. So initial I, the rod is there itself, plus the moment of inertia of the masses. For one mass it is m by 3. M into mass into distance square, and distance is L by 2 whole square. Okay. But there are two masses, so into 2. All right. So this is your I initial and that is your I final. And if you solve this, you will get as ml square by 4. If we solve this, we are going to get ml square by 4. Now we just put the values in the equation. So if you put the values, I initial omega, I final, omega final. So omega final comes out as omega by 3. So the correct option is 1/3 of omega, first option. All right. So this is the last question that we have, and it was asked in 2026, sorry, 2016. Two rotating bodies A and B of masses m into m with moments of inertia IA and IB have equal kinetic energy of rotation. Okay. So we have two bodies, they have equal kinetic energy of rotation. If angular momentums are LA and LB, then who is bigger? LA is bigger or LB is bigger? So there is a formula. Rotational kinetic energy is angular momentum square by 2 moment of inertia. So this is a formula. Okay. All right. So I can write this as LA square by 2 IA. Similarly, here I can write it like this. So what can I say? LA by LB whole square equals to IA by IB. All good? Now it is given that B is more than A, so this is lesser than 1. So from here I can say LA square is lesser than LB square, or LA is less than LB, or I can say that LB is greater than LA. So the correct option here comes out to be option A. So this is what I had prepared for you guys today, students. Today we have done rotational motion in a nutshell. We have seen moment of inertia, we have seen torque, we have seen angular momentum conservation, and we have seen pure rolling. And after that we have solved the previous year questions, 10 years of previous year NEET questions till 2016. We have solved so many questions today. You must have seen that the questions are not very tough. Okay, they are much doable, very simple questions they are asking. So if your concepts are clear, you will be able to answer them, and you will have a very good exam, and you will score very good in this chapter. In this chapter, I'll repeat again, moment of inertia is very important, angular momentum conservation very important, and PO rolling very important. So these three topics are very important for this chapter. And that's all for today, and I hope that your exams go very well, and you all are able to achieve your dreams. Thank you so much. Have a nice day.